So now that we've looked at what intermolecular forces do and how they affect different properties, now we're going to look at the different types of intermolecular forces. So the first one is London dispersion forces. And these forces occur in everything. They're the only force that are in nonpolar molecules, but they occur in polar or nonpolar molecules. So here's what happens in a London dispersion force. So we have a helium atom. There we go. A helium atom. And helium has 2 electrons. And then, so usually the electrons are spread out because they repel each other. So we'll put one here, one here. Okay, so those are the electrons. And let's say that the electrons just happen to come on the same side of the atom. So now they end up over here together. So when this happens, we get a partially negative side, the side that's on the electrons, or with the electrons, and the other side is partially positive. So it's still a neutral atom, but because the electrons happen to be on the same side of the atom, it causes that side to be partially negative. Okay, so, when we have helium, we don't just have one atom, we have several atoms together. So just imagine a balloon filled with helium atoms. And we have another one that comes along, and it starts to get close to this atom that has these charges. I forgot to say this, but whenever that happens, we get what's called an instantaneous dipole. So remember, we learned in chapter 8, I think it was, when we have electrons being shared unequally, we get a dipole, and the dipole goes in the direction of the negative charge. So this is an instantaneous dipole. Okay, so when this atom comes along, and it has its electrons on the opposite side of the atom, but as it gets closer to the atom with our instantaneous dipole, what happens is this partial negative side will repel. So let's see here, whoops. So this partially negative side repels these electrons right here to go to the other side of the atom. So I'm going to write them over here. Okay, so the instantaneous dipole repels those electrons, and now we get a partial negative, and a partial positive for this atom. Okay, so this dipole, because we have a dipole now, this dipole is called an induced dipole. So the instantaneous dipole causes the induced dipole, and now the attraction takes place between the partial negative and the partial positive. So right here, that's where the London dispersion force would take place. So again, if I had another helium atom come in, we could have this happen again. Because again, anytime we're talking about forces and these atoms, we're talking about having many of these atoms or these molecules. Oops. Okay. Here's another example. This one, we have 2 induced dipoles. So we have 2 iodine molecules, and as they approach each other, the electron clouds repel each other, and they form 2 induced dipoles. So that can happen as well. So we have instantaneous with the induced dipole, or we can have 2 induced dipoles occur. So again, the London dispersion force just happens in between the partial positive and the partial negative charges. Okay, there are factors that affect London dispersion forces. We're not up to the factors, just kidding. So again, London dispersion forces are in all the molecules. It doesn't matter if they're polar or non-polar. We're going to see, though, that for non-polar molecules, that's the only force they have. And for the electrons to distort the way they did with the helium atom, it's called, or the tendency of that to happen is called polarizability. And polarizability increases as the molecule gets bigger and bigger. So I can figure out, if I'm just looking at London dispersion forces, I can figure out, which one is stronger based on its size. And I'm going to show you that here in just a second with an example. But all I have to do is look at the molar mass of the molecule or of the atom, and I can tell who has stronger London dispersion forces. So that kind of goes along with the factors that affect London dispersion forces. It says the strength of dispersion forces tends to increase with increased molecular weight. So the larger the atom is, or the larger the molecule is, the stronger those London dispersion forces are, because it's easier for the easier for the electrons to move around because there's so many of them. Also, the shape of the molecule affects the strength of dispersion forces. So just to give you an example real quick. Okay, so if I have C5H12 and I have it in N-pentane, and I also have neopentane. So both of these molecules have C5H12. They're just arranged differently. So this one, in pentane, we would have a carbon chain. And for this one, we would have a ball of carbon, basically. So it looks something like that. Okay. So here you can see there's more surface area. Look at all that surface area there. So if another N-pentane molecule came by, I'd have all that area right there in green to form dispersion forces with that other molecule. But over here on neopentane, the ball, really that's all the surface area I have right there on those two carbons. Over here, over here. So I just have these little spots where it can form London dispersion forces with another molecule. So the shape of the molecule affects how strong those dispersion forces are. So if I have a long carbon chain, the bigger the molecule, then I have stronger London dispersion forces. But if I have a small molecule or small surface area, then I'm going to have weak intermolecular forces or weak London dispersion forces. Okay, so I'm having an example here. It says put the following molecules in order of strength of London dispersion forces from highest to lowest. So all of these molecules are nonpolar. So the only intermolecular force we're looking at is London dispersion. So all we have to do is add up the weights of these molecules and put them in order. So using our periodic table, we can do that. So, man, I keep getting different colors. CH4 is our first one. Carbon weighs 12. Hydrogen weighs 1, and we have 4 of them. So we would get a total of 16 grams per mole. So that's the molar mass. Okay, iodine, we would have 253.8 grams per mole. Oxygen, there's 32 grams per mole. Again, I'm just getting these numbers based on their molar masses on the periodic table. Bromine, we have 2 of them, would be 159.8 grams per mole. Carbon tetrachloride is going to be 153.8 grams per mole. And chlorine will be 68.9. Okay, so now that we have the weights, we can put them in order based on their strength of London dispersion forces. So we'll start from highest to lowest. Okay, so the strongest to the weakest. So all we have to do is figure out who has the largest molecule, and that's going to be iodine. Okay, iodine has a molecular weight of 253, so that's going to be our first one. Okay, so again, this is strongest, strong, and weak down here. Okay, so iodine is the strongest, and then next would be bromine. So bromine has a weight of 159.8. So we'll put that one next, bromine. Okay, and then it's going to be carbon tetrachloride with 153. So we're going to put that one right here. And then we have chlorine would be next, 68.9. And then oxygen with 32. And the very weakest out of all of these would be methane, the CH4, because it weighs the least. Okay, so all you have to do is look up their molar masses and put them in order based on that to figure out who has the strongest, who has the weakest London dispersion forces. And if I have a molecule with the same number of atoms, then I have to look at the